Okay, good afternoon, everyone. My name is Rez Mani, and the title of today's webinar is Laser Testing of Single Event Effects and Case Studies. I work for the company Allied Scientific Pro in Gatineau, Quebec, Canada, and I've given this webinar a number of times and try to modify the webinar every time to reflect the activities of the company in regards to SEE. And I would like to say a few things before I start the webinar to clarify a few things. First of all, the webinar will be recorded and the recording will be sent to you within a few days. And the second point is that our company is not a research institution, so we just make SCE systems. So basically, during the webinar, I'll show that we got some results with some chips that show the single event effect, but we haven't done any testing with complicated devices because we are not a research institute. And finally, the GoToMeeting platform that we are using is really not for sharing videos. It's not meant to share videos, but I still have one video to show. So what I'll do is I'll send you the link for the other two videos that I don't want to show, and we'll also show this one, the one video. So please bear with the quality of the video. So let's move on and look at the topics that we are discussing today. The outline of the talk would be I'll talk about the principles of single event effects and also what are the different types of single event effect, the destructive and non-destructive, or you can call it soft and hard errors, and what is the need for testing of satellite instrument for SCE prior to launch. Then I'll talk a little bit about the radiation testing for SCE, and then I'll move on to the optical testing, which is the pulse laser testing. And that is classified into single photon absorption and two photon absorption. And then I would compare the TPA versus SPA. And then I would move on to introduce our pulse laser C testing system. We have a lab here that is available for rental, and we also make systems. So I'll describe those, talk a little bit about wide band gap semiconductor C testing requirements, and then I would go into case studies where we did some testing on some chips. Of course, the data for SCE behavior of these chips were already available in the literature, and we only did the testing to validate our SCE system. And finally, I'll talk about the commercial SE systems that we built. Uh, at the end, by the way, we have a Q&A session, so you can ask your questions, and so we can discuss any questions you might have at the end. So let's look at the single event effect and why it happens. It happens when a charged particle, for example, a proton or an uncharged particle like a neutron, it hits the circuit, and along its way, when it penetrates through the circuit body, it generates these electron hole pairs. So these electron hole pairs could basically disrupt the operation of the circuit or destroy the circuit. And satellite instruments, as we know, they carry many electronic instruments such as FPGAs, power MOSFETs, EEPROMs, analog to digital converters, digital to analog converters, and so on. And also transistors, op amps, and flip flops. The operation of these devices could be affected by these cosmic rays that are hitting the circuit, these charged particles or uncharged particles. And so care has to be taken to protect the circuit against them. So before the launch, these circuits need to be tested to find if there is any sensitivity at any part of the circuit, and basically think about a redesign of the circuit or doing some radiation hardening to prevent this sensitivity to cause a problem. So let's look at the sources of charged particles in space. Where are these charged particles coming from? So there are three sources. And number one is cosmic rays. So if there is, for example, a supernova explosion somewhere in the galaxy, it could send all the protons and charged particles towards our solar system that it will eventually reach our planet. And the second source is our sun, which emits a huge flux of charged particles, uh, especially during solar flares. And so, some of the charged particles are trapped in the Earth's magnetic field, and they create these Van Allen belts, basically. And when a satellite is traveling through these, it will encounter these charged particles. And the last source would be the secondary particles that are generated when a proton, for example, hits our atmosphere, and it generates these cascades of particles like pions and neutrinos and muons and so on. As you can see here, there is the collision of the primary cosmic rays with our atmosphere. So, for example, airplanes that are flying could encounter these charged particles, or a satellite that is being launched on its way to space could encounter these charged particles. Now, a little bit about the types of single event effects. There are non destructive or soft errors, for example, single event upset, single event transient, single event latch up, and single event functional interrupt. So here you can see, for example, uh, the SEU, the single event upset. So a charged particle has hit the particular cell and has flipped the state from 0 to 1. And over here, another charged particle has, let me actually activate the laser pointer. The charged particle has hit this logic gate, and it creates this inverted pulse that propagates down the circuit. And basically, it's a sequential circuit. So down the line, it could flip another uh, cell from 1 to 0. Then we also have destructive errors, which could be latch up, single event latch up. So latch up could be either non-destructive or destructive, and SEGR, single event gate rupture, and single event burnout. So a little bit more about this. I already explained the single event upset is the state change due to a charged particle strike, and single event transient, the temporary pulse that traverses through the circuit. What about the single event latch up? So there are some parasitic transistors that, when they are hit by a charged particle, could be activated, and this would cause an increased current flow, and the chip would heat up, and it could upset some big bits that may lead to disruption of the circuit operation. So one way to remove this error would be to do a power cycle, and that could fix the problem. But the latch-up always accompanied by high current flow because of these shorting that happens due to activation of parasitic transistors. Then we also have the single event functional interrupt. So that happens when the basically control elements, like control bits of the circuits, are bombarded by a cosmic ray, and that will cause some kind of malfunction in the circuit. But you don't need to recycle the power, and there's no increase in current. Just basically resetting the instrument or reloading the configuration to the register will fix the problem. That's called Cephi. Next one, we talk about the destructive C or hard errors. The first one is single event burnout. You can see in this case, DC to DC converter has been burned, and this happens mostly in power MOSFETs where there is a physical damage to the part. And then there's a single event latch-up, the destructive version, where the current that passed through was so large that it has destroyed the circuit. So even the recycling of the power does not fix the problem. And finally, we have the single event gate rupture, which happens in MOSFETs. And this, I will talk about this later, is the only effect that cannot be um, basically triggered by the optical method. It requires the bombardment by a charged particle. So what happens is that the in the MOSFET the gate is struck by a charged particle and it gets ionized and it shorts the source. Uh, it shorts the source, and basically that's what causes the error. The optical bombardment can sorry the short it shorts the source to the drain, and that's why this happens. The source to drain gets shorted out by bombardment of this gate by the charged particles, and that's how this happens. But you cannot generate this with optical beam because the this requires the insulator in between to be ionized, and this insulator cannot be ionized by bombardment with the optical beam. It doesn't have enough energy. Maybe if you use a UV laser or an X-ray laser, it could ionize the insulator there, but with the normal optical lasers or infrared lasers, you cannot ionize the insulator. There's not enough energy of the photon to do that, whereas the particles could actually do that. So for this reason, SCGR is only possible to trigger with the charged particles and not with the optical beam. Okay, next would be the need for testing of satellite instrument prior to launch. So the sensitive nodes needs to be uh, identified in a circuit before the launch. For example, here this is from a paper by McMorrow that they checked the SCU sensitivity map of a SRAM cell, and the red spots show the most sensitive parts of the circuit, and the yellow are the little bit less sensitive of that. So these parts needs to be mapped and identified. So once these are identified, one has to look at the possibility of redesign to remove the sensitive transistors, or if there are measures like radiation hardening, silicon on insulator, or silicon on sapphire that is required to protect the circuit against the bombardment by cosmic particles. Okay, so let's look at the radiation testing for SCE. Just briefly see how it works. So you can see that a beam of this usually happens in a particle accelerator, and the beam of charged particles are incident on the circuit. So you would mount your circuit inside a vacuum chamber, and then this cocktail of different particles are incident on it. What are the pros of this? First of all, this more realistic of the space environment because, in fact, the particles are bombarding the circuit in this space. It penetrates through metal. We know that there are a lot of metal pieces on circuits, so it's covered by metal, and the particle would pass through that. And you can also find absolute values of saturation cross section, upset threshold, and realistic error rates could be calculated by doing the particle testing. However, there are some downside to it. The cons, basically, it is an expensive way of testing because you need to make an appointment in a particle accelerator, which could take you a few months to get there, and it is quite expensive, thousands of dollars per hour, and the number of facilities are quite limited. So it may take a while before you can actually take your instruments there and do the testing. It could also damage the circuit permanently. It does not penetrate thick protecting insulating layers on devices such as flip chip packaged IC. So here you can see in the flip chip configuration, you have a thick layer of insulator, and the charged particle cannot penetrate through this to reach the sensitive part. You also need to make a vacuum because otherwise the charged particle would collide with the air molecules and it loses its energy. So here is an example of a facility in Finland. You can see this long tube where the charged particles are accelerated by a high electric field, and the circuit is mounted in the vacuum chamber. And basically, these charged particles are incident on this, and the SE behavior is examined. So there's a YouTube video here which I will send you. I will not show you this video, but you can watch that later if you like. And basically, that shows the operation of this, uh, you can say, facility and how this is done. So I'm sending you on chat. You can look at that later if you like. All right, next. Uh, all this pointer options. Yes. So what the testing will provide for you in the test facility would be the graph of cross section versus LET in MeV centimeter square per milligram. I'm sure most of you are familiar with this curve, and this LET is important because it is proportional to the energy, and it actually represents the stopping power, a retarding force acting on the ionizing particle. So the more the energy, the more will be this retarding force. And you need this to calculate the threshold let and also the saturation cross section. So it rises after a certain let and then it flattens off. So from these parameters, you can calculate the error rates, which is required. Uh, so to calculate the cross section, which has dimensions of centimeters square, for an accelerator test, you would divide the number of upsets that are shown here by red squares by the beam fluence, which is in particles per centimeter square, and that will give you the area, the cross section. This is the standard way of doing it. But there is an alternative method, the optical method, where our company uh, offers a system to use this method. And in this case, instead of using particles, we use photons to bombard the circuit. So the system is made of the laser system, basically a few cameras, an IR camera, visible camera to illuminate the chip. The chip is mounted on a positioning system that could move with the submicron resolution, and there's a microscope objective. So the beam, the laser beam is focused by the microscope objective to a dimension of a micron on the device, and it could move on the device. And there's also a illumination system that will lit up the device under test, so you know where your beam is. So what is the pros of this technique? The biggest pro, I would say, is the having the spatial resolution and temporal information that you cannot get with the uh, particle method, because particle method would have a wide beam and you don't know where exactly the this single event effect has occurred, where the upset has occurred. But because this has such a small dimension of a 1 micron, you could actually exactly map where the sensitive parts of the circuit are and where these effects are happening. You can also synchronize the clock of your detector with the laser and make sure that you know when it has happened. So temporal information can also be obtained. The other information and the other advantages would be it's a less expensive system. It can be done anywhere. It doesn't damage the circuit at low energy levels. It passes through thick insulating layers. Like, remember, we were talking that in case of the particle, it doesn't pass through the flip chip die, but in case of the optical beam, it could pass through it. And it's very suitable for COTS testing, commercial off-the-shelf systems. You could buy many pieces and test them one by one. and discard the ones that are not good even before going to your particle facility. So this way you would save money and time, and you would also know what kind of error rates this produces even before uh, spending thousands of dollars for a particle facility. So these are very, very useful. But nothing is perfect, and there are some disadvantages. And the biggest disadvantage is that it does not give you the absolute threshold and also the cross section. So you need to calibrate it at least once at the particle facility. It would not give you the absolute values. It's good for finding the error modes and also discarding the equipment that are not functional and the pieces that are not working. You don't need to do a particle test to find that. So this will be very useful for that. And it does not penetrate through metal. So if you have like a power MOSFET that is covered by metal, you cannot shine from the top. You could do it with the particle, but not with the optics. You have to go from the back side. So this will not go through metal. And one has to understand that this is only a complementary method to radiation testing. It's not meant to replace it completely. Okay, so let's talk a little bit about some basic physics, because this is related to the choice of laser that you will be uh, choosing. So there are these valence band and conduction band. I'm sure most of you know about this. In case of metals, they overlap. In case of insulators, they're wide. There is very big band gap. And in case of semiconductors, the band gap has a moderate uh, distance, or it's not that big. It's moderate. So it's possible for electron hole pair to be generated once it's struck by a particle or a photon, and the electron could jump to the conduction band and contribute to the conduction. So for silicon, this band gap is 1.1 electron volts, and one can translate that into a wavelength. So any wavelength that is uh, above the threshold basically could create this electron hole pair. The 1.1 electron volts, it corresponds to 11, nearly about 1100 nanometers. So if the wavelength of the laser is below 1100 nanometers, it could uh, basically cause absorption by electron hole pair. It could create electron hole pair. And if it is above that, then it cannot, because it doesn't have enough energy to help the electron jump across the gap. So once you do the testing with the optical system, you will get the similar curve, cross section versus the, now you have the energy per pulse in picojoules. So you'll see it's still the threshold energy and then the saturation cross section. You get a similar curve, which you can compare with the curve that you get once you go to the accelerator. So the shapes are very similar, but the x-axis has different units. So to measure the cross section for the optical beam, for example, in a SCU sensitivity map, when you want to produce that in a SRAM cell, you would move the beam, like imagine the mouse is the beam. So you would move it from one point to another, and every time there is a upset, you would basically reset the circuit. Say if it drops from 1 to 0, at this point, you would reset it back to 1 and move to another point, and then if you will see if it causes the upset. And if it doesn't, you move on to the next point. So you would scan the whole circuit like this, and then you will see which points are most sensitive. And you have to do this at different energy levels. So you can see the red requires less energy than the yellow. And that would produce the cross section versus the picojoule curve that you need to calculate the error rates. What about the penetration depth in silicon? It actually increases with increasing wavelength. So at very short wavelengths, 590 nanometer is only about 1.7 micron. But at 1064 nanometer, which is the wavelength of neodymium YAG laser, it increases to 676 micron. So if you like to go deeper and you are doing backside illumination, it's better to use the longer wavelength laser, but the disadvantage is the beam size would be larger due to diffraction limit. So your resolution would decrease. If you want to do a high resolution mapping, it's always better to use a short wavelength like 590, but it doesn't go deep enough. So if your surface, the circuit is accessible from the top, the sensitive part is on the top, and you want to do mapping, it's better to use the short wavelength laser. But if it is not accessible from the top and you want to go from the back side, then you need to have enough penetration depth and you need to have a longer wavelength, but that reduces your resolution. Here is a graph of the absorption coefficient, which is inversely proportional to the uh, basically the penetration depth. And you can see that at 1.16 micron, it drops to zero. So past this wavelength, there is no absorption and no electron hole pairs are created in the normal fashion. I'll talk about the two photon absorption later, but this 1160 nanometer is an important wavelength for the just the normal absorption of photons. So we arrived at single photon absorption, optical excitation of carriers, and here you can see the 590 nanometer is shining and creating the electron hole pair. And this interaction of radiation with matter is described by a set of equations that are shown here. And you can see in the first equation, the rate of change of the intensity with distance or with depth is given by these three terms. It turns out that for single photon absorption, the other two terms, this is a nonlinear term, I square, and this is for basically for free electron absorption within a band. So these terms becomes negligible, and only the term surrounded in the square becomes important and significant. So if you solve the equation only you taking into account the first term, it will just the solution would be nothing but Beer's law, the familiar Beer's law, the exponential decay, which we are familiar with and is given by this equation over here. And the rate of the deposited charges are proportional to directly to the intensity of the beam. So you can see that the beam is very strong at the surface, and then eventually as it propagates through the material, it gets attenuated. Along its way, it deposits charges. The red color represents deposition of charges, and this is called the 1 over E contour. So here, like 63% of the charges are deposited, and the intensity of the beam is reduced to 36% of its original value. So for a 590 nanometer, this is pretty short, less than 2 micron. For 800 nanometer, this is about more than 6 micron. Here again is the picture for the 800 nanometer and the 7 micron optical depth. 63% of the charges are deposited. Okay, the next issue is the effect of pulse width. So can we use any pulse width with the laser to do SCE testing? What are the requirements for pulse width? And there's a very interesting paper by Duane and Pouget that talks about this issue, and it actually divides the pulse width into three regions: region 1, region 2A, and region 2B. The important thing is that uh, the pulse duration should be shorter, should be shorter than the response time of the circuit. So if the pulse duration is shorter than the response time of the circuit, then it does not matter what energy it has. So here, for example, you can see between 100 femtosecond and 30 picosecond, the threshold pulse energy does not vary. It stays constant because it is smaller than the response time of the circuit. When it is more than that, 30 picosecond to 8 nanosecond, then there is a gradual rise with the pulse duration. And past 8 nanosecond, there is a sharp linear rise with the increase in pulse duration will increase the threshold pulse energy. So it's not that you want to you cannot get the SCE with longer pulses. It requires more energy to get that. Typically, you want to use a picosecond pulse so that you make sure your pulse energy is shorter than the response time of your circuit. Then there's also the issue of backside and front side illumination. So in which situation you should use which mode. So if your front of the circuit does not have much metal pieces and you can reach the sensitive parts with the laser does not go through metal, then you can use the front side illumination, and you can use a short wavelength like 590 so you can get higher resolution. But if your top is all covered by metal, such as in case of the power MOSFETs, then the only way to do it will be to go from the back, and you need to make sure you use a long laser wavelength so that it penetrates through the depth of the die at the back. And if it is still not available, if it's not reaching it, you may need to polish the backside or thin it so that it could reach it. So you may need to do some etching or polishing. Now, let's talk a little bit about two photon absorption, the TPA. So what is that and when is it used for? So in case of, for example, 1260 nanometer, it's more than 1160. So the energy of one photon is not enough to excite the electron and create electron hole pair. So in this case, in certain conditions where the energy of the photon uh, basically is in nanojoules, the energy of the pulse is in nanojoules, and the duration of the pulse is in maybe 100 femtosecond or less, then at the focal point of the laser, then two of the photons could put their energies together to excite the electron from the valence band to the conduction band. So two electrons would put their energies together, but this does not happen for any type of laser. The pulse energy should be in nanojoules, and the pulse duration should be in 100 femtosecond region, very short pulse. And what happens in this interaction of radiation with matter is that the third term becomes important. The nonlinear term, which is proportional to I square, becomes important. The other terms become negligible. So the intensity, uh, basically the change of intensity is proportional to I square instead of I, and the rate of deposition of charges is also proportional to I square. So normally photon energy should be slightly greater than half the band gap energy, and this is a nonlinear process that happens. So you can see this effect in a better representation here. So when the beam is shining throughout its passing in the die, it does not create any electron hole pair, contrary to the single photon absorption that is exponentially attenuating. This does not create any electron hole pair. Only at the focal point where the beam is in the micron diameter, then this electron hole pairs are created by two photon absorption. And this provides some huge advantages because you can basically inject the charges at any depth that you would like by adjusting the distance between the microscope objective and the surface of the chip. So you won't get any attenuation along the way before reaching it. You can just inject it directly at the point that you like. and that will also make the 3D imaging possible because you could move on a plane, on an XY plane, but you could also move it in the Z direction to see what is the sensitivity along Z. So you can create a 3D image of this when you use the TPA. And it's also the charge track is more similar to radiation testing, which is another advantage. So once again, let's compare TPA and SPA. The advantages of TPA to SPA: large penetration depths, because you could reach any point without creating electron hole pair along the way. 3D imaging is possible, carrier confinement in focal zone, more similar to radiation testing, and backside illumination is easier. But what about the downside of this? So because you're using longer wavelength, due to diffraction limit, you have a longer or bigger spot, which would reduce your uh, resolution. So your resolution would suffer there. And then there's the high cost of the femtosecond laser. You need a optical parametric amplifier, which I'll talk about later. That will make it more costly. And then the other thing is that your backside should be the backside of the device should be a mirror-like finish. There shouldn't be any inhomogeneity and non-uniformity because that would cause dependence on the square of the intensity would cause some non-uniformity in the beam. So I have to make sure that it's all flat and the beam is sitting flat on the back side so that it doesn't create any non-uniformity due to the dependence on the square of the beam. So if there is non-uniformity, it could significantly change the charge produced in the sensitive volume. So that is a factor that needs to be considered. So the summary of necessary parameters for laser quickly. We talked about the laser and single photon absorption, two photon absorption, the 1.16 micron limit there. Focusing size as a result of diffraction limit increases with wavelength. Uh, and we talked about the pulse durations and the three regions. So for SPA, you could be picosecond. For TPA, typically you're working 120 femtosecond. Um, then we also talked about the fact that the pulse width should be shorter than the response time of the circuit. Pulse energy typically for SPA is picojoules, for TPA nanojoules. Also for depending on analog or digital circuits, the digital circuits usually could trigger the uh, SCU with picojoules, but for SCT, you may need nanojoules. So analog circuits require more energy. And spot size, it could be anywhere from 1 micron to 5 micron, depending on the microscope objective and the wavelength and the focal length. It is limited by the diffraction limit. What is for sure is the smaller the spot size, the higher is the resolution. Okay, so after all this theory, let's look at what is practical and what are we offering. So we have the ASP's laser system. It was first designed and delivered to an aerospace company in the US in 2017. It was an SPA system with the potential to be upgraded to TPA. You could see it was a little bit bulky at the time. It was our first attempt at making this circuit, but this was delivered in 2017. And the system has basically four subsystems. The laser is a fiber laser at 1030 nanometer, and its energy is controlled by polarizers and ND filters and so on. You can see in this block. Then you have the number two, you have the illumination system, which is an IR LED with 1300 nanometer and visible LED at 625. Then you also have the camera module, which is a visible CCD and a SWIR camera. So this will look at the infrared lights and visible lights to see where the beam is on the circuit. Uh, And finally, you have the objective, microscope objectives, and translation stage. So microscope objective, we have it 20 times and 100 times. Mitutoyo objective, high quality microscope objective. And the translation stage is a new port translation with roughly 1 micron resolution. In the vertical direction, we have 30 nanometer resolution because we have the basically some kind of piezo actuator there. And in order to see our system, uh, this is like the diagram for it, but there's a video which I would like to show. And basically, this is our CEO, Mr. Steve Lavoie, is introducing the the system. So I would like to send you this, and I will also play it. So I would play this video so we could both look at our system. This advertisement, past this advertisement, and I will also. Hi, this is Steve at Allied Scientific Pro. I'm the CEO of the company. Today I will introduce you our SCE testing station. So we put together a system in our lab in Canada. So you're welcome to come here to do some tests of your IC chips. And we also build those commercial systems as well for our customers. So we do offer service and also a system. So just a very quick summary of what we have here. So we have an XY stage for a very rough adjustment, all motorized. We also have manual, very fine adjustment with tilts. And we have a very precise focusing stage as well to focus under the microscope objective to see clearly the IC design. Over here, underneath here, you have all the microscope accessories, which is protected for the people. With the microscope objective, we use the Misutoyo for 20x, and we also have a 100x, a very quick release, drop in place, no alignment time. We have two camera. One is a shortwave camera that can see through silicium, and also one visible camera for very quick alignment. And same thing with the light. So we have two sort of light source for illumination of the microscope. One in the visible, one in the shortwave. So you could imagine both spectrum. So the laser is on the lead over there. So in this case, we use a picosecond laser, but this is for a single photon system. But we also offer and build two photon system with femtosecond and the OPA laser. So and then you have a full control access of by computer of all these devices and testing gears. So that's a very short summary of our SE system. So you're welcome for coming here to try it out. Thank you very much. Bye bye. Okay, so this was an introduction of our system by Steve. Uh, so let's look at the specs for our laser systems. So you have the SPA at 1030 nanometer, and its rep rate from one shot to 1 megahertz. And you could attenuate this pulse energy with the neutral density filters and polarizers. Pulse width typically 30 picosecond. For the TPA, you need an additional component. This is the OPA amplifier, optical parametric amplifier, and that will generate anywhere between 630 to 2600. So you would pick a wavelength, for example, 1260 nanometer. It's a 150 to 250 femtosecond pulse width and single shot 200 kilohertz repetition rate. So we have a serviceable lab in Ottawa, Gatineau that we would rent out for customers who want to come and basically test their equipment. And we also build and sell commercial C-grade systems, both SPA and TPA. And you could get in touch with our salespeople and basically get a quote for that. So what about the other material besides silicon? We didn't talk about gallium arsenide, gallium nitride, and silicon carbide. So they have different band gaps, wider band gaps. So they would require different laser for SPA. So the fiber laser at 1030 nanometer would not work for gallium arsenide. Your maximum laser wavelength could be 870 nanometers, so a tie sapphire laser would work. For gallium nitride, you need a UV laser. It has a really wide band gap of 3.4 micron. Sorry, 3.4 electron volts. So 364 nanometer. And silicon carbide, you could use a neodymium YAG second harmonic and different lasers for TPA as well. But we are capable of building these other lasers, although all of our commercial systems that we have sold so far were geared towards the silicon substrate. So let's look at some of the case studies that we did. And as I mentioned at the very beginning, we wanted to choose some samples that whose SE behavior were already in the literature. It's nothing new about it. We just wanted to validate our laser system, SE laser system, to make sure that we are getting the effect. So this is by paper by McMorrow, Pouget, and Buckner, who are all pioneers in the field, and they used this HM6504 SRAM 64 by 64 matrix. And what you see in the red square is one cell of this 64 by 64, which is you can see over here. So these are all metals on top of the circuit, and they started moving the beam, which was an 800 nanometer laser, across and see where it actually causes an upset. And at 4 picojoules, there was only one point where they got the upset. But when they increase the energy to 7.2 picojoules, you see there are more dark spots, and at 10.4 more, and at 20 picojoules more. So they produced these curves for the sigma versus laser pulse energy picojoules. And this is all done within one cell. Okay, so we try to sort of repeat this experiment with our laser at 1030 nanometer. So the first step was to get a hold of a ceramic chip, which we had to decapsulate. You can decapsulate that with a plier. You don't need acid. For plastic cases, you need acid etching, but for the ceramic, you could just use a side snip plier and it will come off. You can see the silicons here, and this is the map for it. You have all the uh, you can say memory cells here. Then you all have the control cells, sense amplifiers, and column decoders right on the top. So 100 micron by 100 micron cell size for one cell. So because our beam was longer, was larger, was about 400 micron, we actually did not do the test for one cell. We illuminated several cells, and I would get into that later. So this is some of the basic components of our system. We mounted the chip on an Arduino Uno board so we could read and write on it. So we wrote with the Arduino code 1 to all the cells, all the 64 by 64 cells. This is our translation stage. In the vertical, you have this other actuator that has a 30 nanometer resolution. And we made a box for switching, basically reading and writing, and also writing 1 or writing a 0. And this is the Arduino software for reading and writing. The control software was all LabVIEW. The microscope objectives, we used it 20 times and 100 times. And what is to be noted here is the 20 times has a wider aperture of 8 millimeters. So the laser beam has a diameter of 8 millimeter when it, or 7 millimeter when it gets to the microscope objective. So all of it will get through, but the 100 times, which has a bigger magnification, would block some of the beam because it has only 3 millimeter aperture. So we used the HM6504. The settings we used was 10 kilohertz, pulse width 30 picosecond, laser wavelength 1030 nanometer, pulse shape was selected as single pulse. Uh, Laser pulse energy varied depending on microscope objective used. And initially, we wrote a 1 to all the cells. The diameter, as I said, was 400 microns, so it was bigger than size of one cell. So we moved the beam around to see how many cells would flip, just to get an idea of what is the sensitivity of different cells on the chip. Here there is a video of all the experiment that we did, which I would like to send you. We don't have time to show this video, but you can look at it later if you like. I'll show you on the, I'll send you on the chat. So you can look at that if you like later. And let's move on to the experiment. Pointer options, laser pointer. All right, so uh, the first test was we doing a SCU test using 100 times microscope objective, 13 nanojoules for pulse energy. So one may ask, why are you using such a big energy for SCU? SCU is a picojoules, but the beam is basically not focused, is defocused to 400 micron. So if you scale that to 1 micron, you get picojoules of energy. And we move the beam in steps of 200 micron along the inverted L track that I've drawn in here. And so the initial value of all the cells was 1. And after we moved this, we did a reread of the whole thing, and we saw that some cells have flipped from 1 to 0. And you can see here in the Arduino software, cell number 719, Q was 1, cell number 720, Q is 0. So Q is 0 where the upset occurred. And also 847 was 1, 848 was 0. And these are the 8 cells that flipped state. So they were clearly upset cells, and there was no increase in temperature, and we could also rewrite 1 on them. So this was clearly an SCU. Next, we used the 100 times microscope objective, and we increased the energy to 60 nanojoules and moved the beam again in this, you can say, uh, invert, this kind of flipped L-shaped, and or inverted L-shaped, you can say. Same parameters, 10 kilohertz, moved by 200 micron. And this time we saw many cells, almost 1/3 of the cells, they flipped state, although some of these flipped states were not even along the path of the illumination. So they still flipped state. And the chip got very hot, extremely hot, which shows a large current, and we couldn't write a 1. So the initial cell value was 1, and then these are all, the red ones all turned to 0, and after we couldn't write a 1, it wouldn't accept that. So the only way to fix that would be to recycle the power, and then we could write a 1 on these 0 cells. So this clearly showed a single event latch up case. Same experiment with the initial value being 0 instead of 1. And again, moving it along this inverted L, we saw these red were all the ones that had turned to 1 from 0. And we couldn't write, again, a 0 on them. We had to recycle the power. The chip got very hot. And this is how we verified the SCL in the 0 to 1 mode. And finally, we increase it to 500 nanojoules. We use a 20 times microscope objective that could has a bigger throughput. So we moved the beam again along this inverted L, and this time more than half of the cells turned from 1 to 0. The initial value was 1. And this time, even recycling the power would not allow us to write a 1 back to these cells, which showed that the cells were permanently damaged. And this is an indication of the destructive cell. So, what is our future plans for this? We would probably focus the beam better to 5 micron diameter and move the beam within one cell to create this cross section versus energy, pulse energy that may be useful information. And maybe we also shine the laser on control electronics. Like here, we showed somewhere that there was these sense amplifiers and column decoders. So if we shine the laser on these, we may be able to detect a Cepheid, which is another form, and also test more complex devices such as MOSFETs and FPGAs is in our plan. The other test study was on LM124. This is an op amp. So we would mount this on a follower circuit. We had a picofarad probe, um, and it actually, this circuit has many transistors, and one of the transistors, Q9, is very sensitive, as was reported in the literature. So uh, basically, the chip was decapsulated, and you can see the bare chip in here, and the laser beam was moved around transistor Q9. And so you can see the circuit is exactly shown here. Here you see there's a Y that is flipped to the left side, and this is a Y that is flipped to the bottom. So this is the same circuit that we are looking at here. So it was easy to identify where Q9 is and shine the laser around that area. And once we did that, we had to also trigger the laser using uh, the sync pulse from the laser. We triggered the scope, sorry. We triggered the scope using the laser pulse, the sync pulse from the laser. And we saw these different pulses of different widths that appeared on the scope. You could look at the exact video and the link that I sent you. So these are clear indication of SET, the single event transient. And finally, the ASP fully installed and commercial SCE systems. This is a system that we built and we delivered to Germany. They were very concerned about the protection and class 4 of the laser. So this cabinet was built around the laser system. And the window is protecting against the laser radiation. So this becomes a class 1 laser when it's inside the cabinet. You can see the laser, the cameras, the visible camera, the IR camera, the controllers, the translation stage here. And this is a SPA system with the possibility of upgrade to TPA. So for TPA, we need to use the optical parametric amplifier. So we are capable of designing both SPA and TPA systems. So finally, we go to the conclusions of this talk. We found out that the SCE laser pulse testing is complementary to radiation method, and basically can never replace it. It is required for measuring absolute cross section. The radiation testing is for absolute cross section threshold, but the laser testing could be for preparation to go to a accelerator facility to find the error modes that you can get and to discard the faulty COTS pieces before going to the radiation facility. So sensitive nodes could be identified, it reduces radiation testing time, and it saves you money. Although TPA requires a more expensive ultra short pulse laser, in some applications where you want to do 3D imaging, it is better to use TPA. Or if you have trouble getting from the back of the chip, you need to traverse through a long distance to get to the sensitive area, TPA is a better option. So it is also more similar to radiation testing because it has very narrow charge deposition. Optical SE testings are faster and less expensive, can be deployed at any location. And finally, SEU, SEL, non-destructive and destructive, were observed for HM6504 SRAM, and SET was observed for LM124 op-amp. Uh, and as I said, these were already verified in the literature. We use these just to validate our laser system. So we did validate our laser system performance by creating these or observing these SCE effects. So this brings us to the end of our talk. Thank you very much for listening. We will also send you a feedback form. Please fill out the feedback form. If you have any suggestions to improve the webinar, anything you want to see, anything you want to be changed, please let me know. I'll be glad to look at all the comments. And at this point, I'm going to ask the audience if they have any questions they can ask. So someone already put, yeah, you'll receive the whole webinar recording in a few days, yes. So are there any questions? You can unmute yourself or you can type. Either way.
Hello, can I ask a question?
Yes, please. Yes, Clark.
Okay, all right. Yeah, thank you, Dr. Mani, for the presentation. Yeah, my question is regarding wide bandgap devices.
Yeah,
What would be the strategy to overcome the bandgap itself? Because I guess it's different, maybe more energy
yeah.
or different wavelength.
Yes,
Thank you.
yes. I did mention something about that. Let me go back to that slide. Let me find that slide. Has to be here. Yes. So you could see the band gap is wider. Gallium arsenide is 1.42 electron volts compared to 1.1 for silicon, right? So we can't use a 1030 nanometer to do single photon absorption. You need to use a different laser. For example, in case of um, gallium arsenide, we recommend the titanium sapphire laser. It's a tunable laser from 720 to 1000. And the maximum wavelength you can use is 870. For gallium nitride, you need to use a UV laser, 364 nanometer. So, for example, xenon fluoride emits at 351. That's a suitable laser for that. And for silicon carbide, you could use neodymium, second harmonic neodymium YAG laser. So the answer to your question is use a different, shorter wavelengths for uh, different larger band gaps. Did I
Okay,
answer your
thank you very
question?
much.
You're
Yeah.
welcome. Yes. Any other questions?
Hello, can you hear me?
Yes, please
Yeah,
go
thank
ahead.
you. I have a quick question. For
Yes.
laser test, you mentioned that it's not good to do the laser test from the metal side of the die. But have
Well,
you
yeah,
ever?
no, it doesn't penetrate through metal. The laser
Yeah,
beam does not penetrate through metal. Yeah.
yes. So my question is that have you have ever any experience that when they do the chip design, they do some metal exclusion on the top, and then this chip is for the laser test from the metal side? Because in the chip design we can exclude some metal from the top.
Yes. So yes, if it is accessible by all means, then you can go from the top. But
Okay.
not every chip is like that. You maybe there's some chip they have taken this into account and they've made that. But not all the chips are like that. Like some power MOSFETs are filled with metal on top. So there's no way you can get to the sensitive part from the top. You have to go
Okay.
from the backside.
Yeah, yeah, yeah. So yeah, so it's still possible when we do the chip design. So
Yes, if you
okay.
do it, then yeah, it's easier to do SE testing with laser from the top. By all
Yeah.
means, it's easier. But
Yeah.
this is most of the cases, I think it's not accessible.
Hmm. Yeah. Thank you.
Yeah, you're welcome. You're welcome. Any other questions? All right. Going once, going twice, going three times. All right. So you will receive the webinar recording if you want to look at it again. Please do so and feel free to ask any questions. My email will be provided to you, and when my assistant sends you the email with basically the form to fill the feedback form, she will also send you the email, my email, so you can email me if you have any questions after watching the webinar recording. Thank you
Hello,
again.
Res. Excuse me, can you hear me?
Yes, yes.
There's one question if you can scroll down on the chat.
Oh, there's one question. Oh, okay, thank you.
Yes.
This question by Idam Hafiz. All right. Can you explain again why TPA is more similar to radiation testing than SPA method? Right. Yes, that's a very good question. So let me go there. Let me go to the TPA. Basically, if you look at the charts, there's a paper by um, uh, Buckner and McMorrow that has a diagram that explains that really well. I can show you that. In fact, if I can show you that diagram, it will be very, very easy to understand that. Yeah, this is the paper by Buckner. So this diagram, which I'm referring to, is this is the diagram. So this is the path of the deposition of electron hole pair when a particle is going through the circuit, okay, down to 10 micron. So you see it's very narrow. It's very narrow and there is maximum charge density at the center, right? But this is for a single photon absorption. You can see there is this exponential decay. So the beam widens as it passes through the material and it gets like weaker and weaker due to exponential decay. For case of TPA, they're more similar to each other. So the the deposition of charges happens in a very narrow region, similar to the particle strike. It doesn't spread as wide as in case of the single photon absorption. It's more confined. So the charge path, the charge deposition path is more similar to um, particle strike. That's the reason why it's more similar there. To answer your question, I refer you to this paper. It's very well explained. Okay, thank you. So if there's no other question, uh, I thank you again for attending this webinar, and I hope to see your comments on our feedback form. And I wish you a great afternoon and stay safe. Thank you. Have a good day. Bye.